Greetings. This is the start of Chapter 6, specifically Sections 6.1 and 6.2. Chapter 6 deals with structures that are made up of pin-connected members. So the example of that structure that we'll work with for the current time, or right now, is trusses. A truss is made up of slender members that are joined at the endpoints. So all the members are connected to each other at their endpoints. And there are a couple of assumptions that we'll make whenever we're working with trusses here. We assume that the loadings on the truss, the loadings are applied at the joints, so they're applied at the points where the members are connected. Here we have a picture of a roof, and it's supported by a truss at each end, and the load from the roof itself, the roof surface, gets transferred to the truss by these purlins, these horizontal members, and the purlins are attached at the joints for the truss. So that fits with our assumption that the loadings are applied at the joints. So here's a figure showing that. And then the second assumption that we make for trusses is that the connections are made with smooth pins, so that is frictionless pins. What these mean, the fact that the loadings are at the connections and their connections are made by smooth pins, is that all the members of the truss are two-force members. So that means that every member of the truss is either in pure tension or pure compression. Because it being a two-force member, the force acts along the line connecting the two joints, so the two endpoints of the member. And we'll examine simple trusses, which is where you have three members together to form a triangle. So, and then you can keep adding triangles to extend the truss. So here's a figure showing a simple truss. We have three members here with a triangle, and then we added on other members to make another triangle. And now to analyze these structures, we need to find the force in each member. And we'll start our analysis with one technique called the method of joints. And it's based on the assumption, or not the assumption, but the thought that if the whole truss is in equilibrium, then every part of the truss is in equilibrium. So we look at each joint because we figure each joint is in equilibrium. So the way this progresses is we draw a free body diagram of each joint, and well, we'll start at one joint and solve for the member forces that connect there, and then we'll go to another joint and solve for those member forces, and we just keep propagating all the way through the truss to get the force in every member. So we draw a free body diagram, and then we will apply equations of equilibrium. So these two force members, there are no moments applied to the member because the forces on the member are collinear. And so we're looking at the joints. So all the forces applied to the joints intersect at a single point, which is the joint. So we have two equations of equilibrium. It's equilibrium for a particle. Some of the forces in the x direction equal 0, and some of the forces in the y direction equal 0. We will now look at an example, and we have a simple truss here, and we want to find the force in every member. So we want to find out if each member is in tension or compression, and then what the magnitude is. So in order to do this, we need to find well, we want to start with a joint. So we need to pick one joint to start with. And so we'll start with a joint where there's at least one known value, one known force, and no more than two unknowns. So for those reasons, we'll start with joint B, because so that looks like this. So we'll look at B, and here's the joint B, and we can go ahead and assume tension for the members. So that's FAB. And then we have 500 newtons applied horizontally. And then we have FBC. Although just looking at it, you can either assume it's in tension, or you can examine it and make a guess, an educated guess as to whether it's in tension or compression. So looking at it, in order to have a force balance in the X direction, this member will have to be in compression. So that's FBC. Right, so equations of equilibrium. And I've decided this marker is not going to work. It's just too fat. So equilibrium in the X direction, we have 500 newtons to the right, and then we have FBC square root of 2 over 2. So that square root of 2 over 2 is the cosine of 45, and that is equal to 0. So we get that FBC is equal to 500 square root of 2. And that is in compression. And then force balance in the Y direction. So we have the sum of the forces is, again, FBC sine of 45, which is square root of 2 over 2. And then minus FAB, and those add up to 0. So FAB is equal to FBC square root of 2 over 2, which is 500, which is 500. So FAB is 500 newtons, and that is in tension. So you want to be sure to mark if the force in the member is in tension or compression. If it turned out that, say, this force was compression, then we should redraw the free body diagram, because we're going to be referring to it when we go to the next joint. So we still need to get the force in member AC. In order to do that, let's go look at joint C, because at joint C we'll have one known force, which is force BC, and we'll have no more than two unknowns. We'll have the unknown support reaction, the vertical force at C, and then we'll have force in member AC. Since we don't care about the reaction force, we can just solve for FAC. So here's the free body diagram. Member BC was in compression, so that means it pushes on joint C. And then here's the vertical force from the support, FC, and autofocus again. Okay, and member AC, just looking at the equilibrium for this particle, this joint, we see that that's going to need to be in tension, because FBC is pushing to the right, so we need some force in that negative X direction. So this is FAB. And then to solve for this unknown, we'll just do the force balance in the X direction. So the sum of the forces in the X is FBC cosine of 45, which is square root of 2 over 2, and minus FAB, and that equals 0. So FAB is equal to 500 newtons, and that's in tension. So that was one quick example where we use the method of joints to find the forces in the members of a simple truss. And now we will look at another example. So one thing that's important is whatever force you have for a member, when you do the free body diagram of one of its ends, you need to draw the force acting in the opposite direction on the other end. So if the member is in compression, for example, it's going to push out on both ends where it's connected. Okay, so right, so there's free body diagram section B. Okay, so here are better figures for that. So if we want to find the forces in the members here for this problem, we'll use the method of joints. And the question is, which joint do we start with? All right, so the rule for looking at a joint is that we want a joint where there's at least one known force and no more than two unknown forces. So which of these joints satisfies those criteria? Joint D has one known force and two unknown forces. So here's the free body diagram of joint D. We've got 300 pounds acting down. FCD are due to tension, and there's a direction for FCD. And then here we'll draw FAD in compression. And so tension and compression for this one I just got by examining it. FCD needs to be in tension to balance the downward force here, and then FAD needs to be in compression to balance the FAD needs to push to the left in order to balance the force to the right from FCD. So we'll do force balance in the y direction first, because that's where the direction for our known force. So we have, oops, I don't know what I just did to the, okay. Excuse me for a second. That's fun. Okay, so the free body diagram for joint B, that's where we were, or D. Force balance in the y direction, we have 3/5 of FCD, and then down is 300 pounds. That equals 0, so FCD equals 500 pounds. And that's in tension. And then we can move on to force balance into X in order to get the force in member AD. And so that's 4/5 of FCD, which we found to be 500 pounds, minus FAD, and that adds up to 0, so FAD is 400 pounds. And that is shown in compression. It came out with a positive number, so that's right. I don't know how to get that line off the screen. I guess I need to figure it out. Let's see. That's not good. Okay. Now let me get to another figure and we'll move on to a new topic. It's still in structural analysis for trusses, but it doesn't have to do with the method of joints. Alright, so this topic is zero force members. It's possible in these trusses that some of the members will have there'll be no force on some of the members. And those are called zero force members. So there are two ways that a member could be a zero force member. And so here we have a figure showing a truss, and there are a couple of zero force members in this truss, and I'll talk to you about the criteria for a zero force member, and then we'll be able to identify them. So this one criteria that's shown here is when you have three members that are connected at a joint, and two of the members are collinear. So if that's the case, where you have three members, two of which are collinear, then the third member is a zero force member, assuming that there's no external force or support reaction applied to that joint. So for example, we look at joint D. That's members DE, CD, and AD. So right here, we have three members coming together at a joint. Two of the members are parallel, one of them's, and so then that means the third member is a zero force member, since there's no external force applied there. And if you look at the free body diagram, you can see that in order to have equilibrium for that point, then this force needs to be zero. Because if it was non-zero, then there would be nothing to keep the point from moving in this direction, since the other two forces have no components in that direction. And then joint C also has three members, two of them are parallel, and there's no external force applied there, so that means the third member is a zero force member. So here's the truss redrawn with the zero force members removed. So that's one way that a member can be zero force. You got three of them, two of them are parallel, and there's no external force applied to the joint. The other possibility is if you have two members, two non-collinear members connected at a joint, and there's no external load or support reaction applied to that joint. There are a couple of these cases in this truss. So looking at joint A, we see two non-collinear members that are connected to the joint, and there's no external force applied there. So we'll look at the free body diagram of joint A, and here are the forces from the members. FAB is horizontal, FAF is vertical, and so if we look at the force balance in the x direction, we see that FAB is 0, and y direction tells us FAF is 0. So for that joint to be in equilibrium, then these have to be zero force members. And can you find another pair of zero force members that is a joint where there are only two members and there's no external force? Joint D meets that criteria. So we'll look at the free body diagram for joint D, and again, these have to be 0, because if FDE was non-zero, for example, then there would be no way for FDC to keep the joint from moving horizontally, because FDC has no component in that direction. So those are zero force members. And here's the truss redrawn with the zero force members removed. So that's good to keep in mind because it simplifies the analysis of forces, or of trusses. So we will do now a couple of examples. Here we want to identify the zero force members in the truss. So I'll draw the free body diagram of the entire truss, showing all the members. So we have an applied force here, we have reactions at E and A, and so here are two non-collinear members that have no external force applied to their joint. So these are zero force members. So we could redraw the truss, getting rid of those zero force members. And so now if we look at this point, point A, it's not exactly what we were talking about before, where you have three members, two of which are parallel, but it's really similar. Here we have these two parallel forces, a force from the reaction and then force in that member. And so this member's force has to be horizontal. So that means that the force in this member is 0. So if we did the free body diagram of point A, we would have force from the support, force from member AB, and then force here from AE. And the force balance in the y direction tells us that FAE is equal to 0. And it's like the condition where we had three members, two of which were parallel, and no external force applied, or no other force applied to that joint. So this is a zero force member. So just redraw the truss again without that zero force member. Now we have the same situation here at point D. We've got two parallel forces and then another one that intersects that joint. So if we did force balance on D, then we would see that member DE has to be a zero force member, this one right here. So the only non-zero force members are shown now in this last figure. So member BE, AB, and BD. Now, we will use what we learned about zero force members to work on this problem here. So this is fundamental problem 6.1, and we want to determine the force in each member of the truss and state if the members are in tension or compression. So we'll use the method of joints to solve this problem. And which joint do we want to start with? Oh, well, before we start, we should identify any zero force members. So can you spot a zero force member in this truss? Okay, the way the truss is loaded now, if we look at B, member BD is a zero force member because we have AB and BC are parallel, and then BD is a zero force member because there's no other force applied to that joint. So let me just redraw the truss without member BD. Well, okay, so we know BD is a zero force member. So now which joint do we want to analyze first? We can look at joint D because there's one known force and there are only two unknown forces. So joint D, here's the free body diagram. We know we have a horizontal force of 450 pounds. BD was 0, so I'm just going to assume compression for AD. FAD is compression, and I'll assume tension for CD. So here we'll have to solve these equations simultaneously, because there's no one equation with only one unknown in it. So the direction of these AD and CD are 45 degrees. So our forces in the x, we have FAD cosine of 45, which is square root of 2 over 2, plus FCD square root of 2 over 2, and then minus 450, and that's equal to 0. And so there's what we get from that equation, and then we'll do the same thing in the y direction, and that just tells us that FAD is equal to FCD, since those are the only forces in the y direction, and they well, I'll go ahead and write it out. FAD sine of 45 square root of 2 over 2 minus FCD sine of 45. So FAD is equal to FCD. So that gives us that 2 times FCD is equal to 450 times square root of 2, and we get that FCD is £318, and that's in tension, and we know that that's FAD is also that, but it's in compression. And okay, FBD is 0. So now we need to get AB and BC. So we'll move on to joint A. And here's the free body diagram. We have a vertical force from the support. We have the force from member AD, and that is in compression. So that means it's going to push on joint A, FAD, and then we have an unknown force, AB, and we can see that that needs to be in tension to balance the leftward horizontal force from AD. And we don't want to have to solve for FA, so we can just do the forces in the x direction. So we have FAB to the right and FAD cosine of 45 to the left, and that's equal to 0. So that gives us that FAB is equal to 225 pounds, and that's in tension. And then if we look at joint B, we just see that FBC is the same. So FAD, again, it's in tension, so it's pulling away, and then there's FBC, so we just can tell that FAD and FBC are equal. So FBC is also 225 pounds. Tension. So that was the method of joints in order used to find the forces in the members of this truss. And that wraps up Chapter 6, Sections 1 through 3. We talked about the definition of these simple trusses and the assumptions. So we had 2 force members and found 0 force members. There are 2 ways a member of a truss could be a 0 force member. This figure here shows one way, and then we used the method of joints to find the forces in the members. Method of joints is basically just drawing the free body diagram of each joint and applying the equations of equilibrium for a particle on that joint to find the forces in the members.